Hi all, welcome to Unacademy JEE English, a brand new channel by Unacademy, India's largest online learning platform for IIT JEE. And here everything is taught to you completely in English. So the topic that we'll be discussing today is electrostatics of a conductor. This topic is very important as far as IIT JEE is concerned. Reason? A huge amount of variety is possible when it comes to questions. Why? Because this is a very tricky and complex topic. So today I'll try and walk you through the key concepts involved and let's try and make it easy for you guys. So before we get started, let me tell you a bit about myself. My name is Rohit Dixit. I've studied mechanical engineering from IIT Delhi. I have 7+ years of teaching experience. I myself was JEE rank holder 447 and I've coached many students to top ranks in IIT JEE. Let me also tell you about the Unacademy subscription and its benefits. You have live classes, you get to interact with your educators, you have live polls and leaderboards, test series and analysis, which is very important for your self-testing. Then you have live doubt clearing sessions, again, a very important plus point. Then, most of all, you have access to India's best educators. Don't forget about that. All right. So, here are some easy steps to get the subscription. You install the app, then you go to JEE, select plus, then there you select your goal as IIT JEE and get the subscription. Now you can use my code RDLive to get the subscription. This code will get you 10% discount immediately. All right. So let's get started with the topic of the day, electrostatics of a conductor. So first of all, we need to understand what exactly conductors are. Now, conductors are objects which allow the flow of electricity easily through them. Now, how are they managing that? That is because they have something called free electrons. So, what are free electrons? You know that every matter is made up of atoms, and in every atom there is a nucleus, and nucleus has positively charged protons and neutrons, right? And then there are electrons which keep revolving around this nucleus. Now these electrons are bound to this nucleus. When I say bound, it means they can only keep revolving around it, they cannot move away from it. The reason for that is the electrostatic attraction between the positively charged nucleus and the negatively charged electron. However, in certain objects, when you talk about the outermost electrons, they are not so tightly attached to their nuclei. So let's imagine two nuclei, one here and another one here, right? And let's imagine an electron revolving around this nucleus. So imagine during its revolution when it comes here. Now here, it is feeling the attraction of this nucleus as well as the attraction of the nucleus adjacent here, right? So this electron, because it's not very tightly bound to this nucleus, what happens is that sometimes it will jump to the adjacent nucleus and start revolving around this. Now, that is what a free electron is. Free electron is not bound to a single nucleus. It will in fact jump maybe to this nucleus, and while revolving around this nucleus, it can jump to another nucleus. So free electron can freely jump from one nucleus to another. So this is a picture that shows you. Right, in this picture, you see a swarm of delocalized electrons. When I say delocalized electrons means that they don't have a fixed local position, they keep moving all around. And that is why you essentially see an electron cloud there. So though these electrons can freely move inside the volume of the conductor from one nucleus to another, they will not be able to leave the surface of the conductor, right? And they can't just fly out. Why? Because all these positive charges will effectively hold it from flying out. Inside, yes, they are free to move around, but they cannot leave the lattice. All right. So let's see how the conductors behave without any external electric field present. In such case, this electron, when revolving, I said it can jump from one nucleus to another. Now, which nucleus should it jump to? Now, it should not have any preference. There is no logic why it would prefer jumping to one particular direction, right? It can jump to any direction. Now, that jumping is completely by chance. So, it happens to jump to any nucleus at any time. It could have jumped here, it can jump here, it can jump here, it can jump anywhere. So, imagine a lot of free electrons jumping from one nucleus to another. Now, by chance, they are jumping. So, because of that, what happens is that the motion, entire motion, if I look at the entire motion of electrons jumping from one nucleus to another, so that becomes completely random because somebody might be going this way and some other guy might be going that way, right? There are so many electrons that the overall motion of free electrons becomes random. As a result, you see that there is no bulk movement of charges anywhere. So overall, you see there are electrons jumping all around, but still you don't see any charge movement, overall charge movement happening, right? And you also don't see any charge accumulation happening anywhere. Imagine a condition where there is this nucleus and every free electron starts jumping to this. In that case, you would have seen a negative charge being accumulated here. But since this jumping is completely random, there is no charge accumulation happening anywhere. And since there is no charge accumulation happening everywhere, everywhere feels like a neutral place, even though the electrons are jumping constantly. And since every part is neutral, you don't see a net electric field anywhere inside the conductor, right? So you can see in the figure also, these free electrons are jumping randomly from one nucleus to another. Now let's see what happens when you place a conductor in an external electric field. Now you see, there's an external electric field pointing in this direction. So this field starts applying an electrostatic force on all the charges present in atoms. So on the nuclei, on all the electrons. However, all the nuclei are firmly fixed to their positions. Though they feel the force due to this electric field, they cannot go anywhere. So same happens with most of the electrons. The only guy who can move freely was free electron. Now earlier, before this field was applied, this free electron was jumping here and there randomly. Now what happens when this field is switched on? Now this field pointing in this direction will apply a force acting in this direction to free electrons. Why? Because electrons are negatively charged. So negatively charged electrons will feel a force in this direction. As a result, what happens is when it is revolving around one nucleus, now you realize the tendency of jumping on the other side becomes lesser and the tendency of jumping this side is much higher because of the additional force of the external electric field. As a result, you see now the jumping is not random anymore. Now you see a net motion of free electrons happening in this direction. Now they will keep on jumping from one nucleus to another, but what happens when they reach the surface? Now they have nowhere to go. So they get stuck there. So what you see is, did you see negative charges start appearing on this surface? Now since these electrons have come here, as a result, a positive charge will start appearing on the opposite surface. Now you will also realize negative charge here, positive charge here, it will create its own field. These charges will start creating their own fields and this field will be in this direction, which is opposite to the external field. You can see that in the picture. And as more and more charges accumulates on these surfaces, this internal electric field keeps on getting stronger and stronger. Eventually, there will come a point when this internal electric field will become strong enough to cancel out the external electric field completely inside the conductor. Now, once this happens, what you say is, now imagine an electron which is somewhere here. Now, this guy will feel no net electrical force, right? Why? Because the force of external electric field would be cancelled out by the force of internal electric field. Now, this guy can go back to jumping randomly. And the moment these electrons start to jump randomly again, now you see that no more charge transfer is happening to any of the sides. So charge accumulations will happen for a bit, and once the internal electric field is strong enough to nullify the external electric field's effect, now there is no net charge movement happening anywhere. This is what we call an electrostatic condition. Electrostatic, why? Because there is no charges moving anymore, right? So let's see what happens when the electrostatic condition is achieved. So first of all, we say that the net electric field inside the volume of a conductor is always zero in an electrostatic condition. How can I say that? Let's assume otherwise. Let's assume there was an electric field inside the volume. So here's my conductor and let's assume there was some kind of electric field. I don't know the direction, but there was an electric field at any point. So had there been an electric field here, it would have forced free electrons to move, right? And free electrons would have started moving in the direction opposite to that of this electric field. So I would have seen charges moving, but I already said we are talking about electrostatic condition. Electrostatic condition means there is no motion of charges. The only reason why no charges are moving is that there is no field present. So that is a logical conclusion. Now, once we have this, we know that the entire volume of the conductor will become equipotential. See, you have to follow it all. This is all logical. It goes step by step. Once you realize that there is no electric field inside the volume of the conductor, now second result is very easy, that the entire volume has to be an equipotential region. Why? Because now when I move one charge from one position to another, the amount of work required is zero. If the amount of work required there is zero, which means potential difference between 2 points is zero. The potential difference between 2 points being zero implies that they are at the same potential. And the points that are at same potential are called equipotential, right? So I can say that the entire volume of the conductor in electrostatic conditions is equipotential. Also, there is no net charge at any point inside the volume of the conductor. Now we'll go ahead and prove it. Alright. Next we can see that any net charge. Now any net charge may appear by two methods. Either you give it a charge or you place it in an electric field by the presence of an external charge or somehow, and that external field will cause charge accumulations, right? So any kind of charge, net charge that you will see appearing can only happen on these surfaces, right? Why? Because we discussed earlier that there can be no charge inside the volume of the conductor. Now let's see why. So here's the proof. We imagined a conductor and then we arbitrarily selected a Gaussian surface. Now, for this selected Gaussian surface, I can see that the closed integral E dot dA has to be 0. Why? Because I already discussed that the E inside the conductor everywhere must be 0. If the E is 0, E dot dA becomes 0 at every point. If E dot dA at every point is 0, the closed integral will also be 0. And from Gauss theorem, we know that this closed integral is equal to charge enclosed by epsilon naught. So if this is 0, our conclusion is that the charge enclosed has to be 0, which means there can be no charge accumulation anywhere inside the volume of the conductor, right? So I said there is no E inside the volume of the conductor. But what happens on the surface of the conductor? So there I already know that there is a charge accumulation happening. But I know that in electrostatic conditions, I'm saying that the net E at any point on the surface of the conductor will always be perpendicular to the surface. How do I say that? Let's imagine otherwise. You can see in the figure. I imagine a case where the surface is like this and E is pointing like this. So this E will have two components, like one component being perpendicular to the surface, another component being along the surface. Now the perpendicular to the surface component will try and pull charges, let's say up or outside the surface. Now these charges cannot leave this lattice, so they cannot go in this direction. So they are stuck here. But what about this field? This field will try to push this positive charge in this direction. Now, there is nobody stopping it from moving from here to here, right? Because inside, they can jump easily from one position to another. So, had there been a tangential component of the electric field, you would have seen that these charges would have started moving here, right? So, since I already said that we are talking about electrostatic condition. Electrostatic condition means that no charges are moving, right? So, the only way that charges would have stopped moving was if there was no component of electric field which was tangential to the surface. So the only possible component is perpendicular to the surface. That is why I'm saying that the net E at any point of the surface will be perpendicular to it. Now, once I know that, the second conclusion that I can make is that the entire surface of the conductor has to be equipotential. Why? Again, by the same logic. Imagine the surface of a conductor and imagine I'm trying to move a charge from here to here. Now, when I'm trying to move a charge from here to here along the surface, that is, what will be the work required? It will be 0, right? Why? Because the electric force everywhere is perpendicular to the surface and the motion is along the surface. So the angle between the force and displacement is 90. So work is integral of F dot ds. So dot product will become 0. So the work required to move a charge along the surface of the conductor is 0. So if the work required is 0, I know that the potential difference between any two points will be 0. So since the potential difference between any two points is 0, I can say that all the points on of the surface are at the same potential, or in other words, equipotential. Right. Next I'm saying is that the magnitude of net E at any point on the surface will be equal to sigma over epsilon naught. Now I'm talking about the magnitude here. I already said the direction is perpendicular to the surface. How about its magnitude? What I'm saying is that the magnitude will be sigma over epsilon naught, where sigma is the charge density at that given point on the surface. So let's imagine there is a surface. Now here the E might be different, here E might be different, but if I want to find out the E here, so how can I get that? The magnitude will be sigma at this point, in this area, wherever I'm trying to find the magnitude of E. So sigma of this point upon epsilon naught being the permittivity of free space. Now how's that? Let's go ahead and prove it. So in this example, I've taken an arbitrarily shaped conductor and I've imagined a Gaussian surface which is shown by blue. So let's try and find out closed integral of E dot dA over the Gaussian surface. I know that this cylindrical Gaussian surface will have three phases: one circular phase lying outside the conductor, one circular phase lying inside the conductor, and then there is a curved surface, right? So let's talk about the circular phase lying inside the conductor first. For this part, what is the integral E dot dA? It will be 0. Why 0? Because inside the conductor, electric field at every point is 0. So for every point, you will realize that E dot dA will become 0. So for this entire circular phase which lies inside the conductor, integral E dot dA is 0. How about the curved section? As far as the curved section is concerned, now there are two parts. One lying inside the conductor. So here obviously we know that E is 0, so E dot dA will be 0. How about the curved part lying outside the conductor? Now here, as discussed earlier, what is the direction of E? That is perpendicular to the surface, right? And what is the direction of dA vector here? It is like this. Again, you see that E vector and dA vector are forming 90 degree. As a result, for the curved part lying outside the conductor also, the integral E dot dA will reduce to 0. So the only component of E dot dA left is from the circular face lying outside the conductor, this one, right? So here I know the electric field is in this direction. dA vector also points in that direction. So the integral of E dot dA for the entire closed surface becomes E times dA, right? Now from Gauss's law, I know that closed integral E dot dA equals charge enclosed upon epsilon naught. Now I've shown a small area dA of the conductor that is enclosed in our Gaussian surface, right? So what is the charge enclosed? Charge enclosed would be the charge on this dA, right? So the charge enclosed will be sigma times dA, sigma being the charge density at this point, right? So when I equate EdA with sigma dA over epsilon naught, I get E equals sigma over epsilon naught. I hope this derivation is clear to everybody. Please go through it once again because this is very important. All right. Next, let's see some more properties of conductors in electrostatic conditions. One, I can say that potential at any point in the volume of the conductor will be same as the potential on the surface. So I've already discussed this separately. I've said that every point inside the volume will be equipotential and every point on the surface will also be equipotential. Now I can also go ahead and make a small jump and say whatever is the potential on the surface of the conductor, that will be the same potential at any point inside the volume also. Why? Because imagine a point with a charge which is kept on the surface of a conductor, right? Suppose here, and I want to move it to a point which is inside. Now, while trying to move this from here to here, what is the amount of work required? Zero. Why? The moment I am below the surface, the electric field is zero. So when I try to move this charge from surface to any point inside the conductor, the work done is zero. Since the work done is zero, the potential difference between any point inside the conductor and that of the surface is also zero. So I can say that the surface of the conductor, the entire surface will have one potential and the entire region inside the conductor will also have the same potential. All right. So please remember that this will help you a lot with a lot of problems where you have to find potentials, right? Do not forget this. Next thing that I can see is that electric field lines will always be discontinuous at the surface of a conductor. How can I say that? So let's imagine some electric field lines coming like this. Now I know that electric field cannot enter the volume of the conductor. There will be no electric fields inside the conductor. Why? We have already discussed that. So any field lines will either have to terminate on the surface of the conductor or originate from the surface of the conductor. So they will become discontinuous at the surface of the conductor. Please remember that. Again, a very important point. Now, now comes the important part. Now is the tricky part on which most of your questions are based. The charge distribution on conductors. So I've divided that into two categories here. First, we'll talk about charge distribution on conductors where there are no cavities present, and then we'll take up the case where there are cavities inside the conductor. Right. So the first part, let's talk about the key features. Right. Conductors with no cavities. One thing that I can say is that the net charge given is always going to appear completely on the surface. Now we have already discussed the logic of that. There can be no charge inside the volume of the conductor. Any charge, if it appears, will appear only on the surface. Right? Now, how does this charge distribute itself on the surface? So first thing is, if this charge is free to distribute itself, what do I mean by that? That means there is no external influence affecting the distribution of this charge, which means there is no external electric field. Suppose this is an isolated conductor. Isolated means there is nobody else influencing its behavior. So if I give it any charge, this charge is free to distribute itself. It will distribute itself in a way which it likes. So what I'm saying is that when the case is like that, when the charge is free to distribute itself, it will follow a law wherein sigma will be inversely proportional to r. So if you want to see how the charge is getting distributed on the surface, so let's say I'm talking about this point. So what is the sigma going to be on this point? Sigma being the charge density at this point. So I'm saying that if you compare two parts of a conductor, let's say like this, so this being flatter and this being more curved, right? So here, because it's flatter, I can say the radius of curvature of this part is higher and the radius of curvature of this part is smaller, right? And sigma will be inversely proportional to r. So this part will have a higher sigma and this part will have a lower sigma. Why is that? That happens to make sure that the entire surface is equipotential. I can derive that also, but that's the logic behind it. All right. I hope everybody knows what radius of curvature is, by the way. Right. Okay. So what happens when there are external influences, there are external fields? So I can easily say that in case there are external electric fields present, then this charge will distribute itself to ensure that E inside the volume of a conductor is zero. Right. Now it is not free to distribute itself in any which way. Right? Though the E in both the cases inside the conductor will be zero. But earlier it was choosing the law sigma inversely proportional to R. Now it will have to adjust its distribution so that it can cancel out the external field at every point inside the conductor. So please remember the difference. Right? Do not apply sigma inversely proportional to R for any case. That is only when there is no external influence. Right? When the conductor is isolated. All right. Now let's talk about the charge distributions on conductors with cavities present. Right. So first of all, there is no. First, let's take the case where there is no charge placed inside the cavity. So in such a case, what happens is that you will see that if you have a conductor with a small cavity, you have two surfaces now, right? One is outer surface and another is the inner surface. So I said, though there can be no charge accumulation inside the volume of the conductor, charges can accumulate at the surfaces. So first case, I'm not placing any charge inside the cavity. Now, will any if I give such a conductor any charge, will some charge appear on the inside walls also? And how will it distribute? So in such a case, I will realize that any charge given will come completely on the outer surface only, and there will be absolutely no charge coming on the internal surface. Why so? I can easily see that with the help of Gauss theorem. Okay. You can assume an arbitrary Gaussian surface, a Gaussian surface which lies entirely in the volume of the conductor but which encloses the cavity. Now you know for this Gaussian surface again, the E dot dA integral will be 0. So that gives us that the net charge enclosed inside has to be 0. So that means there can be no net charge appearing on the walls of the internal walls of the cavity, right? As a result, there will be no electric field inside the cavity also. So if you have a conductor and if you have a cavity here, now suppose this conductor was initially neutral, all right, and you suddenly got a charge near it. So this charge will start inducing some charges on the outer surfaces of this. As a result, you will see fields, electric fields outside the surface of the conductor. However, bringing this charge, though creates fields on the surface, will not create any field inside the cavity. The field inside the cavity will still be zero. Why? Because there is no need for any charge accumulation there. Whatever was the field of the external charge, that is already being cancelled on the outer surface by the outer surface charges. So since there is no field entering this, so there is no reason for any charge accumulation inside also. Now, let's take a different case. In this case, what we are going to do is we are going to place a charge inside the cavity. Now what happens? The first thing I say is a net charge which is equal and opposite to the total charge present inside the cavity will appear on the inside surface. Now why is that? Suppose this is the cavity and you place a charge here. Now this charge starts creating electric fields and these electric fields are going towards the surface. Now you know that there cannot be any electric field inside the volume. So which means these field lines need to get terminated. So to terminate these field lines, a charge will have to appear on the inside cavity. And how much charge? Equal and opposite. Why so? Because whatever be the number of field lines which are originating from this charge, right, all of them have to be terminated at this boundary. So whatever charge q you keep here, if you keep plus q charge here, a minus q charge has to appear on the inside wall so that it can terminate all the electric field lines which are originating from this, so that no electric field gets into the volume of the conductor. Okay, so what happens in this case? The outer surface, I already know that inside the volume there will be no charge. Now inside the inner walls there is charge. So to compensate for this, now this new charge is accumulated here. To compensate for this, a some charge must come on the outer surface. How much charge? The amount of charge that will make sure conservation of charge. If, let's say, our conductor had a charge earlier, let's say I already had Q1 charge given to the conductor with the cavity. All the Q1 I know from my initial discussion would have appeared on the outer surface. Now I keep a small plus Q2 here. So this plus Q2 will cause minus Q2 to appear on the inner walls. Now you see minus Q2 is here, and the total charge of this sphere has to be still Q1, right? Because it had initially Q1 and there is no way that the net charge of this conductor can change. So the outer surface will now get a charge of Q1 plus Q2, right? Everybody following that? All right. Now the charge distribution on the inside will be determined by the position of charge inside the cavity. That is very important. Suppose there is a spherical cavity, completely spherical, and if I place a charge completely in the center, now what happens is that the field lines that are originating everywhere are equal in strength, right? So everywhere on the surface, equal amount of field is reaching. So a uniform charge will appear. Now what happens when I displace it? When I keep it near of the center, near one of the ends, if I move this charge from center and move it to this position, now you realize that this portion will be receiving a higher electric field. So to cancel all those field lines, a higher amount of charge will appear here and smaller amount of charge will appear on surfaces which are farther away from this charge. Alright. So let's assume initially that this conductor that we are talking about was initially neutral. Alright. And there are no external charges present. So when I place a charge Q inside, and let's say I made it move off the center like this. So I already discussed minus Q2 will appear here, and the way that minus Q2 will distribute itself is that it'll have a higher charge density close to the surface and a smaller charge density away from the charge, right? So as a result, since minus Q charge has appeared here, a plus Q charge to compensate for this has to appear on the outer surface. Now, how does that distribute itself? The field of this charge placed inside the cavity is getting terminated here. So the field reaching to the outer surface is zero, and there was no other external field. So there is nobody to influence the distribution of this charge. So this charge will get distributed uniformly irrespective of where you place this. So you could have placed the charge inside the cavity at the center, or maybe here near any of the edges. Any movement here would have changed only the distribution of the charge on the inside wall. The outside charge on in all these cases will be uniformly distributed. It will follow the sigma is inversely proportional to R factor. Why? Because there is no external influence on it. Right. So let's go over some important points that we have discussed today. The electric field due to any charges present outside a conductor will never reach a point inside the cavity. For that matter, at any point beyond the outer surface. So if this is a conductor, if there was a charge here, any electric field lines will just terminate here. It will never be able to go beyond the outer surface. So if you have a cavity here, the field of the outer charge will never reach here, right? Thus charges outside the conductor can have no electrical influence on the space inside the cavity, right? Now, similarly, we realize that the electric field due to any charge present inside the cavity can also never reach any point outside the conductor. So when I had a charge placed here, all its electric field lines were getting terminated right inside by the inside walls, right? So the electric field due to this charge will never reach any point outside. Why? Because theoretically speaking, I can say that any field that this would have caused at any point outside the conductor will be cancelled by the negative charge or the opposite charge appearing on the inside walls. So the electric field of this charge will be compensated by electric field of this opposite charge at any point outside the conductor. For that matter, any point outside the cavity also, right? So hence I can say that a conductor divides space into electrically isolated regions. What do I mean by that? Electrically isolated regions, that one region, let's say outside the conductor, whatever electrical activity is happening here cannot have any effect inside the cavity. Similarly, I told you when we were moving the charge inside the cavity to different positions from center to here, all that was doing was moving the charge, changing the charge distribution inside the cavity, but it has no effect on the charge distribution on the surface. Similarly, it will have no effect on any charge lying outside the conductor. So that is what I'm saying, that these two spaces are electrically isolated. They are separate. They have no effect on each other. So this result is what we call electrical shielding, right? Have you heard of electrical shielding? You know, whenever there is lightning and all, and if you are in your car, it is said that you should always remain in your car, and in case of a lightning kind of a weather, you should never step out. Why is that? Why is how is lightning happening? Lightning, you know, is an electric phenomena, and you know your cars are made of metals, which are conductors. So when you're sitting inside your car, you're actually sitting inside the cavity of a conductor. So as long as you keep sitting inside, any electrical phenomena happening outside your car will never affect you. So you're out of danger. You're safe there, right? So that is what electrostatic shielding is. So remember, what happens in case there are multiple cavities inside a conductor? Let's say a conductor has a lot of cavities. Now each cavity itself becomes an electrically isolated space. Now none of the cavities can influence each other electrically. You know, whatever is happening in this cavity, let's say, will be by whatever charges are present inside this cavity. No charges outside this cavity can influence anything happening inside this cavity. So if you have multiple cavities, all these cavities and the volume outside the conductor, all of them become separate electrically isolated segments. All right. So remember that. That's a very important thing. Now you can also note one small little thing. That suppose there's a cavity here, right? And there was in an outer surface, and there's a charge placed here. Now, let's say I don't have this charge, all right, and I have given some Q1 charge to the conductor before keeping any charge in the cavity. So all this Q1 would have appeared on the outer surface, all right. So because of that, what is the potential at any point on the surface? It would have been AQ over AQ1 over R, right? Now, what happens when I place a charge of plus Q here? Let's say, for the sake of simplicity, in the center of the cavity. Now, should this influence the potential of that? The answer is no. Why? Because when you place this charge, let's say plus Q2 here, a minus Q2 is appearing here. The net charge on the outer surface is changing, right? However, if you think about it, what happens? Is the field of this charge Q2 reaching any point outside the conductor? No. Since the field of this charge is not reaching any point outside the conductor, which means all the field that is being created outside the conductor is still due to the charge Q1, right? Q1 plus Q2 actually fine, but this guy's field exactly is not reaching there. So when you talk about the potential at any point outside, it will not change, or it will not have any effect due to this guy. All the potential would be because of the charges appearing on the outer surface only. Right? Why? Because the effect of potential also gets cancelled by the charges induced in the inside cavity. Right? So just like the electric field of this charge at every point outside was getting cancelled by the electric field of these charges appearing inside the cavity. By the same logic, similarly, any contribution to the electric potential also of this charge to any point outside the cavity is getting cancelled by the charges appearing on the inside walls of the cavity. So any potential at any point outside this cavity or outside the conductor will be because of only the charges appearing on the outer surface. All right. So remember that. That will also help you in your problem solving. All right. So let's go about some examples. I've taken up only a few simple examples right now. You guys can uh, try and solve some more problems later. So let's just quickly go over a couple of simple examples. So let's try and find charge distributions in the following situations. So here you have a shell, and inside you have a plus Q charge which is placed slightly off the center. and you've been asked to identify the charges appearing on all the surfaces. So this is how it looks. You can see that the inside walls are getting a charge of minus q, right? And the outside surface is getting a charge of plus q. This that minus q that you see outside is actually meant for the inner wall, okay? And you see that the electric field lines inside the cavity are skewed. They are not uniform. Why? Because the charge is off center. However, the electric field lines outside the surface are uniform. Why? Because the outside charge plus q will be uniformly distributed. All right. So let's take up another example. So in this example, I have two cavities. In one cavity, I have plus q1 charge placed, and the other cavity, I have minus q2 charge placed. And let's assume that the conductor itself was electrically neutral. All right. So in such cases, the inside walls of the first cavity take up a charge of minus q1. Right? Why? Because a charge of plus q1 was placed inside. So to counter all the electric field lines, to stop all the electric field lines originating from this, from entering this volume, a minus q1 appears on the inside walls of this cavity. How about the second cavity? In the second cavity, I kept a charge of minus q2. So to stop this charges field, a charge of plus q2 will appear on the inside walls of this cavity. So I see that minus q1 appearing on the inner walls of this, plus q2 appearing on the inner walls of this, and overall my conductor was electrically neutral. So as a result, what happens to the outer surface? A charge of plus q1 minus q2 appears on the outer surface, right? I hope this was easy to follow. All right, let's check your understanding. So in the first problem, I have a charge of plus 3 coulombs placed in the hollow cavity inside a large chunk of metal which is electrically neutral. What is the total exterior charge on the surface of the metal? So I've given the options of 0, minus 3, plus 3, and depends on the shape and position of the cavity. Now the answer is very clear. It is going to be C, plus 3 coulombs. It's not 0. Why? Because the moment I keep plus 3 microcoulombs here, minus 3 microcoulombs will appear on the inside walls. And since the metal or the conductor was electrically neutral, plus 3 has to appear on the outer surface. Right? So do not make the mistake in this. Next, I've shown you an arbitrarily shaped charged conductor. So I've already told you that we have given some charge to this conductor, and all this charge must have come to the surface and distributed itself. So which is the point out of ABCD which has the least charge density? And you've been told that there is no external E present. So there is no external E present. Then you know how the charge distributes itself. It follows sigma inversely proportional to R. Right? R being the radius of curvature. Now you see point B, that is flat. Point B is flat. So what's the radius of curvature of a flat part? It is infinite. Right? So the charge density on that part B will be the least. It will be 0. Right? So till now, I think we have covered most of the basics, and till now you would have certain idea or a fair amount of idea about how charges start appearing on the surfaces. So I'll probably try and make another video wherein I'll talk about specific cases. What are the common specific cases that we get in questions? You get spheres, 2 concentric spheres, 3 concentric spheres, or you get parallel plates and charges, how the charges appear on parallel plates. So in my next video, I'll be talking about that. Till then, you try some problems with the knowledge of this video and let me know how it goes. All right. So again, please remember, you can get the Unacademy subscription with some easy steps. All right. Don't forget to subscribe to Unacademy. It has a lot of benefits. And please remember, you can use my code RDLive to get 10% instant off. All right. So do not forget to use RDLive. And if you thought that this video was helpful and you liked it, then please like and share this video. Also, keep pressing that bell icon. Again, the notes or the slides used in this video are also available in PDF format. So feel free to download those. So one last time, my referral code is RDLive. You get instant 10% off if you register for the Unacademy subscription with this code. So good luck, happy problem solving, and that's it for today. Thank you.